now that we have a little bit of background on light, we're going to talk about the atomic emission spectra. And so we get this phenomenon called the atomic emission spectra because of how electrons are arranged in an atom. And so electrons like to be so that their energy is low. They are most stable when they have a low amount of energy. And we refer to this as the ground state. That would be the lowest energy state of an atom. If energy gets added to the atom, it is absorbed by the electrons. And then the electron moves to a higher energy level. The higher energy levels are quantized, meaning atoms can't absorb a random amount of energy. They can only absorb quantities equal to the difference between two energy levels. So basically it's saying, like our brick building example the other day, you can't move up this brick wall by anything other than one brick at a time or two bricks at a time. There's no stopping in the middle. Another way to think about it is if you're on a ladder. Well, it's kind of a weird looking ladder, I guess. If you're on a ladder, your feet can only touch and only stand on the rings. There's no halfway point here. You have to land on a ring or a rung. And so that's the same thing here. The electrons, they can't stop in the middle. They have to land on one of these rungs. And so that's what it means by quantized. So an excited energy state is when an atom's potential energy is higher than that of the ground state. So when you think of ground state, always think of this one as the most stable and oftentimes closest to the nucleus. And so when an electron returns to the ground state, energy is released or emitted. So when we have an atomic emission spectrum, this is a pattern of lines formed when the light emitted from an atom passes through a prism to separate into its different frequency the light contains. So what can happen, and a way to identify various elements, is to almost burn them or give them enough energy so that the electrons go from the ground state to an excited state. And when that happens, it's absorbing energy. And once it absorbs that energy, it can only sustain that for so long. And so the electrons will fall back to the ground state once that energy is gone. And as it falls, it will give off light energy. And this is what we see when that happens. What you can notice is that different elements give off different frequencies of light. And so when we put those lights, so one of these gas tubes could take place right here, and it goes through a series of slits and then a prism, and then that in that prism the light bends and will be displayed on a black screen. And this is what we get our atomic emission spectrum is right here. And so this is, I believe, for hydrogen, tube containing hydrogen gas. So hydrogen gives off, it's not even on here, various colors when it's split. And so it's one way to identify when you see a purple, a blue purple, a green, and a red on an emission spectrum, that indicates to you that was hydrogen. And so each element that is capable of doing this has its own unique emission spectrum. And like I said, it's a way to identify which element it is. So this led to the development of the Bohr model of the atom. Sometimes this gets referred to as the planetary model. And this says that the electrons surround the nucleus in paths that we're going to call orbits. The ground state is when the electron is in the orbit closest to the nucleus. And as you move away from the nucleus, the electron enters higher energy states. And so they're more excited. The electron is not allowed to occupy the space in between the orbits. So remember that whole ladder thing. That electron has to fall on one of the rungs of the ladder. So when an atom absorbs some quanta of energy, the electron will move from the ground state to an excited state. The ground state we refer to as n equals 1, which would then be closest to the nucleus. And an excited state could then be represented by n equals 2 or n equals 3, n equals 4, etc. The energy gained is the difference in energy between the two energy levels. And so right here we show that. So E2 would be the excited state, and E1 is the ground state, and we can figure out how much energy is here and how much energy is here and subtract them. And so if you want to look at it in the planetary model form, your n equals 1 is in this first ring around the nucleus, and then your n equals 2 is out here. And again, we can use Planck's formula, notice Planck's formula right there, to help figure out how much energy is in each of these ground states, or not ground states, but each of these energy levels. This difference between E2 and E1 right here, we call delta E, or change in energy. So remember, delta really means change in. And it's a change in something. And in this case, because there's an E after it, and E represents energy, this is a change in energy. So the emission spectra are not equally spaced. And this can be explained by the Bohr model if we assume two assumptions. First, we have to assume that the energies of various electron orbits are not equally spaced. So that means that the distance from n equals 1 to n equals 2 is not the same amount of energy as n equals 2 to n equals 3. So there's different distances between energy levels. And the second assumption is that as electrons get further from the nucleus, the difference in energy between successive orbits gets less and less. So Bohr was able to mathematically figure out the possible electron transitions for hydrogen. So remember, hydrogen has 4 spectral lines, and so what he was able to find was, these are all in this graph right here, these are all the possibilities. So we could have an electron go from the second energy level down to the first energy level. It could start up at the third, down to the first, or start at the fourth, down to the first, fifth, sixth, seventh, down to the first. And that would be your Lyman series. The Balmer series starts at n equals 3, goes down, and they all end at that second energy level. And the Paschen series ends at the third energy level. And the Bracken series ends at the fourth energy level. And what he found was that the 4 visible spectral lines, so this purple, the blue, the green, and the red, corresponded to transition from higher levels down to this second energy level. And so what he found was that these electrons were starting in the third, fourth, fifth, and sixth energy levels, and when they fell, we got these colors. So when it started at the 6th energy level, we got purple. The blue came from the 5th energy level, The green came from the fourth, and the red came from the third energy level. But they all ended at that second energy level. And so he called this the Balmer series. The energies released by the Lyman series, they're much greater transitions because they drop all the way down to this first energy level. This results in spectral lines that show up with much higher energy in the ultraviolet region. The Passion series and the Bracket series, these both release smaller amounts of energy compared to the Balmer, and so these are usually in the less energetic infrared series on the electromagnetic radiation spectrum. And so what his big contribution was here was that the Balmer series, we could figure out that this is where those electrons were falling from down to that second energy level. So Bohr's model was great. However, it only works for atoms with one electron. He couldn't predict the spectral lines if there was more than one electron involved. So this pretty much just works for hydrogen. Everything after that has more than one electron.